Hello everybody and welcome back to Chem Talk, where today we will be talking about the adiabatic process. So what is the adiabatic process and how does it vary from other processes that we know? So the adiabatic process is a thermodynamic process which includes the transfer of heat, which is where there is no heat exchanged from the systems or the surroundings during expansion and compression. Now, this process is actually reversible and irreversible. So you can either compress heat and then go back to expanding this heat, or you could expand the heat but then go back to compressing the heat altogether. Now, in order for this process to occur, there must be two conditions met. So the first condition is that the system must be completely and perfectly isolated from the surroundings. There can be no transfer of heat, which means that if the system is perfectly isolated from the surroundings, the transfer of heat cannot occur. And the second condition is that the process must be quick to allow heat transfer from internal energy to take place. So it must be quick so that the heat does not transfer to the system or the surrounding, depending on where it's coming from, and so that the heat from the internal energy only transfers to complete the work of the system or the surrounding. Now, how do we express this equation? So on the screen right now, we're going to see that there is sort of a chart being drawn, or like a data graph, and this is going to express the expansion of a gas, right? So here at point 1, we're going to see that there's pressure 2 at volume 1 at a temperature of T1. We're going to see that this point goes down to our second point, and it goes down to P1, our volume V2, and our temperature T2. So that means that all three of these constants change in order to achieve our expansion. Now, the expansion curve equation is written as P times V to the power of R equals C. So P is our pressure in the system, V is our volume in the system, R is our adiabatic index, and C is the constant that we're looking for between the expression of expansion and our compression. Now, R can either be found in the back of your textbook, or you can just look it up on a source that usually has these kinds of values. So you're looking for credible sources from scientific organizations, such as ChemTalk. Now, we're going to see over here that there's a little bit of a diagram being shown of what is exactly happening in our chart above. So we're going to see that we're going from state 1 to state 2. So in state 1, we see that there is a huge compression of our gas. Our gas is in a very small volume, and that is expressed as V1 and as pressure 2, right? And then we're going to go all the way down to our pressure decreasing, and it's going to go to P1, and our volume is going to V2. Our volume is increasing, and our pressure is decreasing as well. And that means that we're going to state 2. This is how we can visualize seeing our gas being decompressed or expansion. During all of this, we need to remember that the total heat of the system stays constant. So no matter what is happening, whether or not our internal energy is changing into our work, or if our work is staying as work and internal energy is staying as internal energy, we need to make sure that our heat in the system stays constant. There is no heat lost while this is happening. It is all staying as the same no matter what form it takes. Now, there is a bit of a difference when it comes to expansion versus compressions of gas. So when it comes to expansion and compression, both of them have no heat interactions between our systems and surroundings, which is a constant that must be present when we're doing our adiabatic processes. But when it comes to expansion, our work is done on the system using our system's internal energy. So when expansion is occurring, our system is doing the work in order to increase the volume and decrease our pressure. During compression, the work is done on the surroundings by increasing the internal energy of the surroundings. So this means heat is applied to our surroundings, and that is how compression is occurring inside of the system. Now, the surroundings are influencing the system, but that does not mean that our system and our surrounding have any heat interaction. So during our process of compression, we're going to be decreasing our volume while increasing our pressure and our temperature, which is what causes the compression of gas. Now you might be learning about the isothermal process as well, which is also dealing with expressions of expansion and compression of gas. Now you might be wondering, what is the difference between these two and why would I use these two differently? Now, isothermal process occurs at a constant temperature, and the work is done by changing the heat constant of our system. So this means that we are changing the C that we found in our graph earlier. That constant is actually changing in an isothermal process, and our temperature is staying constant. Unlike in our adiabatic process, we are changing the temperature and there is no heat transfer between our system and our surroundings. The work that is done is completely done by using our internal energy of systems or surroundings, and it really, it depends whether or not we're increasing the temperature or decreasing the temperature in order to influence our internal energy to do the work that needs to be done. So, as a reminder, isothermal, there is a constant temperature. Adiabatic process, we are changing temperature and there is no heat transfer, which means our heat constant is kind of staying the same. Now, how do we apply this to real life? You might be wondering, how can I really visualize this, and what is something that I can kind of try out in real life? Now, you can get yourself an ice box and some ice, or you can kind of imagine it. So imagine you're putting some ice in an ice box and you're completely closing it. So that means that the internal system is completely and perfectly, in a perfect world, isolated from our surroundings. So when the ice box is closed, there is no heat transfer from inside the box and the outside of the box. So in order for the ice cubes to melt inside of the box, the energy that is present inside of the box must be used, or else the ice stays frozen. Now in the diagram, that, kind of simple of a diagram, but it gets the job done. So we can see here that between our system and our surrounding, there's no heat in or out because the system is completely and perfectly, again in a perfect world, isolated from our surroundings, which is outside of the icebox. And because you need a little bit of heat influence in order for our internal energy to complete the work to melt our ice will completely stay frozen. Now, you might be testing in this in real life and you might be thinking, oh, well, the ice is kind of melting. Again, in real life, when you're comparing this to a theoretical process, it might not stay the same, but ultimately, our ice will stay almost completely frozen, or it should just not melt at all. So that is what an adiabatic process is.